Alright then, maths notation. The beginning of this book starts with this little quote from this dude called, it's actually a funny name, Robert Record. And he wrote something in 1557. Right at the beginning of this thing, he wrote, "To avoid the tedious repetition of these words is equal to," and then he went and invented the equal sign. Look, it's right there. So the whole point of mathematical notation is to avoid the tediousness of writing out all these things. So what we need to do is make sure that we're happy with what these symbols mean and we can use them properly. So let's begin this by learning maths notation that we need to use. You see, I often tell people that mathematics is all about problem solving to do with quantities. So this dice here, it's got loads of numbers on it. It's actually a 120-sided dice from 1 through to 120. But they're only whole numbers. These are the integers. So we can write this as a set of numbers. And that's what we're concerned about in maths, sets of numbers. And there's a load of different various sets of numbers that you need to know. I'm going to write them down, and then we're going to explain them. So if you start off with absolutely nothing, you get what's called the empty set. This is just 0. It's just 0. And we write sets usually as in these curly brackets, but this symbol here is what means all of that. So the next one is natural numbers. These are just your whole numbers like 1, 2, 3, 4, but not including 0. You write that as an n, but with 2 lines down the diagonal. So this is 1, 2, 420. Okay, but what if you want minus numbers and 0 as well? Then in comes the integers. This is a z. Now it seems a bit unusual that it's a z. I remember this by it being zintegers. Don't know why, always have remembered it by that. So this is everything from 0, plus or minus 1, plus or minus 2, and so on. Now we get into the more interesting ones, the quotients. Now quotient is it's a word that we don't use too much, but it's just like rationals, fractions, that's all they are. So Q with a line down one side, sometimes you see it with a line down both sides, but that way's nicer. Quotients, that's things like a half, a third, 4/5, or top-heavy fractions like 7/3, and so on. That can go on forever. Now, what you might have noticed is we don't have any decimals in any of these yet. So if you have a number that can't be expressed as a fraction or a whole number, then it has to come into this group called the real numbers. So things like a third as a decimal is 0.33333. That's in here. 0.5 is in here. Pi is in here because that is not represented as a fraction. Pi is actually what's called an irrational number. These are sometimes called, probably can't read this, rationals. So pi is irrational. E is irrational. And that's all of those numbers. In maths, pretty much every number that you come across can be called a real number, unless you're doing complex maths. And now a complex number doesn't come up in A-level maths, but it does come up in things like further maths. It's the square root of negative numbers. Sounds a bit bananas, but that's what these are. So square root of -1. And you write that as an I, because it's imaginary, it's not real. It is real, actually. It's used in physics and engineering and really actually quite cool. So once you've got them, you want to actually use them. The way that you use them is by saying, well, we've got some variable, like x, and it's a member of one of these. So let's talk about the dice. Let's say we've rolled our dice and we've got some number, we're calling that number x. how can we actually express this? So x, now they're all integers, so we're going to write this symbol here. That means is a member of. Z, that's the integers. Then we're going to do a colon. That means such that. So x is part of the integers such that it's greater than or equal to 1, but less than or equal to 120. And because it's a set, we're going to do it in curly brackets like that, e.g. If you ever wonder what these are called, they are actually just called curly brackets. That's all they are. This set though, you could say that this is, we're going to call that set A. We might have another set, which is B, and that could be a regular six-sided dice. So we might say x is so we've got the same situation, but now we're going from 1 to 6. So we can combine these two sets of numbers with these symbols, union and intersection. I've just written it out here. We've got union, it looks like a U, it's a union, and N is intersection. On a Venn diagram, the union is all of this and all of that. The intersection is just this bit. Simple as that's it. And it's really nice to do that in maths because you can summarise things pretty quickly. Oh yeah, and we also mentioned this. Well spotted, this was wrong. Should be that. So now we know what numbers we're actually talking about, we can start to do maths with them. Now the number one thing that I mentioned earlier about maths, equal signs. So let's really go through these slowly, so then we've got them for certain. You probably already know them, but let's just do them, okay? Okay, so we've got equals right at the top. If you've got something where it doesn't have an equal sign in it, if it's got none of these, then you've just got a mathematical expression. X squared by itself is just an expression. If you said x squared equals such and such, you've got an equation. And that's from that, made by Robert Record. After that, we've got this sign. It's 3 lines, like an equals, but there's 3 of them. It's equivalent, but it's also known as identical. It's an identity. The difference is equals says that in some situations we have, like x equals 4. That's x is only equals 4 when x is 4. However, equivalent is when something is always true. This is like a difference of 2 squares. Can you see that there? Yeah, of course you can. Difference of 2 squares is always identical, always equivalent. Not bad, eh? Then we've got not equals. That's when something is just not equal something. Greater than or equal to, and then very much greater than. This is good for when you're doing small angle formulas. If you flip them around the other way, then you've got less than and less than or equal to, or very much less than. Simple as that. Now something that's really important here is this. This as an identity is very important to remember, because in maths you get given identities. Ones like sine squared theta plus cos squared theta equals 1. That's always true, no matter what angle you put into that equation, it's always true. And that's true because of Pythagoras. To follow on from these, we've got these things called implies. And these are symbols where, when you're doing your lines of algebra, you write one thing implies another or is implied by the next thing when you're doing manipulation between lines. For example, if you had x equals 4, so our example from earlier, we can say that implies x squared equals 16. But you can't say x squared equals 16 implies x equals 4, because x could have been minus 4. So if we had that, x was equal to plus or minus 4, then you could do this. You get that? Now these are really important. So let's just quickly define these properly again. So this is what we've got. Now these are really important as well. You often get questions in A-level which is like putting the right symbol between these equations, and you have to know, or the 1 mark questions and it says if Q is this and P is this, then choose one of the 4. Now it's quite tricky to get used to this, but as long as you follow this rule, you're golden. Once you've got all them, you can start doing actual mathematics, and there are a few little symbols which can save a lot of handwriting. Now these are really simple ones, like instead of saying such that, or for all x, or there exists an x such that for all x. And when you finish a proof as well, or saying therefore. So let's get them. Okay then, so these little cheeky ones down here, these are your extra bonus ones just to make your handwriting and your general maths a lot quicker. If you were then writing therefore, or this is an end of proof, rather than saying, I have finished my proof, or this is a contradiction, you can do this little, like, it's like a hashtag kind of symbol. This one is like a V with a little gap in it, which means for all. So you could say, this is true for all X, member of reals. Ha! Bam! And then there exists. You don't actually use that too much in A-level, but at uni it comes in quite useful. And another little cheeky one. ST means such that. Going back to here, this colon here is also such that. But that's only when we're using set notation. Now there's one very important one to come. Instead of writing this, we can also use something called interval notation. This is really simple, where you use squared brackets or curly brackets. So if you have, if you've got X is a member, and you write it like this, maybe you do curly brackets here, X is a member of A, curly bracket, really I should say curved bracket, because those are curly brackets, curved bracket A, comma, B, curved bracket. What that means is that X is greater than A and less than B. If you instead use squared brackets, now this is the same again, but less than or equal to. And doing that can save an awful lot of time, especially if it's a combination of 2. So like here, X can never be A, but here it can be. You can mix it up and you can put squared bracket, and that becomes that. Or you can just leave it as all the same. So, your key points. This is set. Set notation. Your implies, your identity. Wicked. That's it. All right. Once we've got this, we're going to move on to doing proofs. This actually makes you really literate in the sense of mathematics, and it's really good to use these. So just copy them out. Make sure you've got them. We're good.